Okay, hi everyone, this is Chang and welcome to OneClass livestream. Today we're going to talk about some of the very popular asked math problems, and let us get started. So here's our first problem, and this problem is asking us to use the definition of concave or convex functions to check whether the following function is convex, concave, strictly convex, or neither. So let's get started. First, when we see this function, it is important to note that this is not a circle. This function is not a circle, although it might be tempting to see this function as a circle at first. So why isn't this function a circle? So a circle is basically x squared plus y squared equals to r, but where this r is a constant. However, in this case, we have x1 squared plus 2x2 squared equals to y, where this y is actually another variable. It's not a constant, so this is not a circle. This is actually a multivariate calculus. So first, let's say note, or let's zoom out a little, so we can have more room. All right, I guess let's zoom in a bit. So let's zoom in and write, or I guess we should zoom out instead of zoom in. So let's say that this is multivariate calculus, which basically is just a fancy word saying that there are more than one unknown variables. So usually you have your just like one normal variate functions, or it's in the form of y equals x something, or like only one. You only have like x as the variable, but now you have like x1, x2. So let's write it down, y equals x1 squared plus 2x2 squared. So let's write it in the form of how you normally see those kind of functions. So normally those kind of functions is written in the form of f of x and y. So you might see those kind of functions written more often. So when you first see the function y equals x1 squared plus 2x2 squared, you might be a little confused, because usually those kind of multivariate functions are written in this form versus the form that was written in question. Sometimes people doing physics write them in this form, so it's more like it's seen more often in like scientific fields, versus here the form is seen more often in the field of mathematics. So I'll just do this question, use the form f of x and y equals x squared plus y squared, because this is just like how you do it easily in my opinion. So now let's do f of x y. This is basically just saying that we're taking the derivative of our function with respect to x, because we have two unknown variables. So usually for functions with just x, so for functions in the form of f of x, you do f prime of x and you just have one derivatives. But in this case, we have the function of f of x and y, so we have two derivatives. One of the derivative, or we have two first derivatives, and one of the first derivative with respect to x, and the first derivative with respect to y. So let's just write them both down right over here. So let's first to take our derivative with respect to x. In order to take our derivative with respect to x, we just look at y squared as a constant. We just see y squared as a constant, or we see y as a constant, so y squared is a constant. And just take the derivative of x squared as how we normally do for x. So the derivative of x squared is 2x. So you just have 2x plus y squared as our derivative with respect to x. Oh, I'm really sorry. Our derivative is actually 2x because y squared is seen as a constant, so, which is equals to 0 if we're going to differentiate it. So the function, our first derivative with respect to x for our function is just 2x. Next, let's look at our first derivative with respect to y. Again, we're just seeing look at x squared as a constant, and y squared we just differentiate normally, so it's 2y. I'm actually a little bit sorry because it's actually the function x squared plus 2y squared instead of x squared plus y squared. I copied down the function wrong. So if we're going to take the derivative of 2y squared with respect to y, it's just going to be 4y right over here. Perfect. So this is our derivative. This is our first derivative with respect to x and first derivative with respect to y. Next, let's look at our function f of x and y. So this is actually our second derivative. So basically, this second derivative is we have 4 second derivative for those questions. So we have the derivative. So basically for each of our first derivatives, we differentiate each of our first derivatives with respect to x and y each again. And so we have 4 second derivatives. So let's just write down second derivatives. F of x, of x, y, and y of x, y. So these are the 4 of our second. So let's write down 4 of our second derivatives. So our we're taking our first derivative and we're deriving it with respect to y again. So since we have our 2x right over here, and we're differentiating with respect to y, since we're differentiating with respect to seen as a constant, and the derivative of a constant is just 0. Similarly, when we're taking our first derivative with respect to y and we're taking that function to differentiate with respect to x again, since we have 4y and that is seen as a function, if we're going to, that was seen as a constant, if we're going to differentiate it with respect to x, so 4y, we differentiate 4y with respect to x, it's just 0, because 4y is seen as a constant, and the derivative of a function, the derivative of a constant is just 0. Next, let's differentiate our derivative with respect to x, and let's differentiate that with respect to x again. So the derivative of 2x is with respect to x, it's just 2. And next, let's differentiate our first derivative with respect to y again, and we're differentiating it with respect to y, which is just basically differentiating 4y with respect to y, which is just 4. So now we have the 4 of our second derivatives. So let's just write down here first derivative and our second derivative. And let's write down a question in full. Concavity. Okay, so now we have 4 of our second derivatives, and we just need to find the Hessian matrix of the second derivative of our function. So in single variate calculus, or when we have functions in the form of y equals something x, we just find the second derivative of our function, and if our second derivative of function is positive, then it's concave up. If it's negative, then it is concave down. In this case, but for our second derivative, but for our multivariate calculus, we have for a multivariate calculus with 2 unknown variables, we would have 4 second derivatives, and you wouldn't know which second derivative you're going to use. And what we have instead of our second derivative is something called a Hessian matrix, or Hessian matrix, depending on how you say it. So our Hessian matrix. And a Hessian matrix is basically taking, this is the notation for Hessian matrix with a big H and in front of f of x and y. There are some different notations of how you write Hessian matrix, but this is the one that we're going to use, and this is the most common one. And what it does is that it puts all 4 of our second derivatives in a matrix, and you have f of x of xy first, and then f of y of x, and you need to make sure that this is the y is first and the x is first, or the x is second in this notation, and because right over here you swap the order of x and y, and these two numbers are actually, or in this case they are the same, they have the same value, but they are actually different derivatives, or they're different second derivatives. So you need to put the order correct, or else it's just bad form. And the teachers would probably mark you down, because this would probably deduct mark, because this is more advanced calculus, so your teachers would probably going to be more strict than before. So next we just copy our answer, or from here down. So we have f of x and x, which is 2. They're both 0, and we have f, which is 4. And next, you might see some people just write it down this way, but I'm just using the 2 lines, or 2 vertical lines, because this actually means the determinant in linear algebra. So this is basically meaning that you need to find the determinant, which is a value or of another function depending on your exact second derivative of the function. So in order to find the determinant of a 2 by 2 matrix, we just multiply these two numbers together minus the product of these two numbers. So we just do 2 times 4 minus 0 times 0, which we have 8. And we know our number 8 is strictly larger than 0. So our 8 is strictly larger than 0. Okay, there's something wrong with my OneNote again. But basically, the answer is 8 strictly larger than 0. Since 8 is strictly larger than 0 for the Hessian matrix of our function, then we know that this function is concave up. So let's say this function concave up. Okay, my eraser stops working again. Concave up. So concave up. And concave up is just another way of saying strictly convex. Or I guess actually say strictly concave up, but so our answer is strictly convex, or f of x, y is strictly convex. I'm not going to write it down in full because it's kind of hard for me to write down here, but basically just write your explanation as we talked about. So we know our function f of x, y is strictly convex in this case, because convex is concave up and concave is concave down. And I prefer using the word concave up because it just makes more sense geometrically, and it's easier to remember than the word convex. But since the question asked us in terms of convex and concave, we can just say the function is strictly convex. If it's larger than or equal to 0, you can say that it's convex, but it's strictly larger than 0. Our Hessian matrix here is strictly larger than 0, so you can just say it's strictly, so you say it's strictly convex. Alright, Now let's do a quick review on how we approach this problem. So first we identified that the function is strictly, first we look at the function and we realized or identified this function to be multivariate calculus with two unknown variables. So based on here, we know that in order to find whether the function is concave, convex, strictly concave, or strictly convex, we need to find the Hessian matrix of this function. So in order to find the Hessian matrix of this function, we differentiate our function with respect to x and with respect to y to find their first derivatives. And then we differentiate each of the first derivatives with respect to x and with respect to y to find the four of our second derivatives. Next up, we just use the four of our second derivatives we found to calculate the Hessian matrix, which is the simplest way to do that is by rearranging our four of our second derivatives of our function in specific order in a Hessian matrix, and you need to make sure that you put them in the correct order. Then we just find the determinant of this matrix that we have here to find the value of our Hessian matrix. If this value is strictly larger than 0, since our value is strictly larger than 0 in our case, we know that this function is strictly convex. And that's how we found out the concavity of our function right over here. It is a little long, but it's actually quite straightforward, or the concept is quite straightforward. And this is a side note, but let's just draw. I'm pretty bad at drawing, or I guess I'm just pretty bad at, drawing those kind of things. So let's just draw our graph. So our graph looks something like here, with it centered on, so this is kind of like the shape of our graph. Whoopsie. The shape of our graph is centered on Okay, I am really bad at drawing 3D stuff. But you see the idea. So this is approximately what our graph looks like. You can see that it's in the form of x squared equal plus y squared, which is a circle. And you know that x squared that f of x comma y is a variable, so that can take any value. And you also know that r squared equals to x squared plus y squared, where r squared is the radius of a circle. So you can see our graph here is actually a lot of circles stacked together on top of each other, and their radius is changing. So yeah, this graph actually makes a lot of geometric sense in my opinion, and that's kind of the beauty of calculus, that it makes sense geometrically so that it is very easy for your brain to understand. Yeah, cool. It's just a side note to help you appreciate more the beauty of math if you are kind of interested in math, or just to help you memorize and understand your math problems further, so you can be better at the test, since that's the reason that you're watching this video, right? Now let's look at our sample solution to make sure that it's correct. And it is. So this basically is just differentiating with respect to x1, which is our x in our question, and their x2 is our y. We just used y instead of x2 and x instead of x1. They forget to write the 1 here, but it's just a small problem. And they forgot, and they wrote the 2. They're supposed to write their 2 on the bottom instead of on the top. And this is just another way to write the first derivative with respect to x. And this just doesn't make sense at all, because the 2 is supposed to be at the bottom. Okay, and I'm not sure why they said that they're, oh, okay, I see. Yes, they said that there's second derivative with respect to their second derivative, or one of their second derivatives is 0. But here they wrote their Hessian matrices wrong, because these two there should be in different order. So for our term over here, the x1 is supposed to be in front, and our x2 is supposed to be on the back, which is correct. But for over here, the x1 and x2, their orders need to be switched because the x2 is supposed to be in front over here. Okay, let's just say first two lines are the x's, the x in the notation, with respect to x1 and with respect to x2 in the first two lines are incorrect, and the Hessian matrix is incorrect. Please add the Hessian matrix notation in front of the second last line. And also the Hessian matrix on the third term. And please also okay, and let's just say right over here, the final solution is correct. I should probably add this another line over there saying that the final solution is correct, but it is alright since we already kind of like missed the question, or not like missed the question. I guess I'll go back and change it. So let me just quickly go back. I hope this works. Nice. Oh, it doesn't. Okay, fine. If it doesn't, it doesn't. Because the form is already submitted, but it's alright. So let's move on to our second problem over here. Our second problem number two. Our second problem is to use a calculator, paper and pencil, or mental math to solve this equation. Or I guess we can quickly use mental math to map down how we would approach this problem. So here we have m, and it asks us to solve the equation, meaning solve for the unknown variable. So our m here is unknown variable. You want to solve for m, which is minus 2 over 9 on both sides of the equation. So on the right hand side of the equation, we just have m, and we have successfully isolated the variable. And on the left hand side of the equation, we have 5 over 6 minus 2 over 9, and you need to find the common denominator of 5 over 6 and 2 over 9. I think their least common multiple is 18, so we just times 3. So we just multiply 5 over 6 by 3 on both the top side and bottom side, which is 15 over 18, and we multiply 2 over 9 on both the top side and the bottom side by 2, which is 4 over 18, and we have 15 over 18 minus 4 over 18, which is 11 over 18. Perfect. They have the same solution, and that's kind of like how we did this problem. But I guess let me just write it down for you. For a calculator, you can just directly type 5 over 6. You can just type 5 divided by 6 in brackets minus 2 divided by 9 in brackets in your calculator, and you can get your answer. Now let's look at pen and paper, which is how we normally do our problem. This is more like drawing pad and laptop, but I mean it's the same idea. Okay, so we need to isolate our m, so let's just minus 2 over 9 on both sides of our equation to do. So we have the following. Next, oh, whoopsie. Next, we have our m on our right-hand side of the equation, and we need to like find a least common multiple, and we know that 6 times 3 is 18, so it's 9 times 2, and that's why we're multiplying 3 for 5 over 6 and multiplying 2 over 2 by 2 over 9. Okay, and then we just do our product calculation here. So on the numerator we have 5 times 3, which is 15. On the denominator we have 6 times 3, which is 18. For our second product, on the numerator we have 2 times 2, which is 4. On denominator we have 9 times 2, which is 18. So on the left-hand side of our equation, we have 15 over 18 plus 4 over 18. Or sorry, I wrote down the sign wrong. It is minus. So on this step we have minus. So on the next step we also have minus. Next step also have minus. Yeah, you'll be surprised to see that I actually make much less mistakes doing mental math than on pen and paper, which is really odd because it should be the opposite. Or maybe probably just because I'm bad at talking while doing math at the same time. But because I was always thinking about the next step in my head while I'm writing the previous step, so it's hard for me to be in sync. Okay, so for our second last step, we have 15 over 18 minus 4 over 18. So since the denominator is the same, we just do the subtraction of the numerator, and 15 minus 14 is 11. So we have our 11 over 18 right over here, and our m, the value of our m is 11 over 18. All right, that's how I do this problem. Next, let's look at the sample solution. They had the excellent solution that is perfect and correct. Let's just say perfect. Your solution is correct. Okay, solution is correct. Now let's move on to our third problem. Okay, so our third problem is actually 1, 2, 3, 4, 5, 6. It's actually 6 problems. Whoa, that's a lot. Okay, so let's do our third problem, or I guess let's do our 3rd to 9th problem. Over here, this is a place where you really need some cheat sheet. I don't know whether you really need some cheat sheet, but that is a lot of trick, in my opinion. So let's do 41. And it's asking us to write the first trigonometric function in terms of the second second for theta in the given quadrant. So we're writing the first function in terms of the second function for the angle in the given quadrant. Okay, I see. Okay, so for our question number 41 here, we're writing tan of theta in terms of cosine of theta for theta in quadrant 3. Okay, so the first thing to note is that our tan of theta is actually equals to sine of theta over cos of theta. This is kind of the first identity or prior knowledge that you gotta know. Let's just write it in blue. I write our solution in black. So this is kind of the first piece of information that you have to know. Next, we're writing our tan of theta in terms of cosine of theta. So we need to find some way to write our sine of theta in terms of cosine of theta. Then we can have a tan of theta in terms of cosine of theta alone. So let's try to find a trig identity that helps us. We can probably use the Pythagorean identity, where sine of theta squared plus cosine of theta squared equals to 1. So this is our I always spell Pythagoras wrong for some reason. Okay, Pythagorean identity. This is actually our most commonly used Pythagorean identity out of 3. So you probably have seen it somewhere, and if you haven't, here you go. Okay, so this is the next thing we should use. So we just rearranged the order of the equation, and we minus sine squared from both sides of the equation. So let's just do, I'm getting ahead of myself. Oh, see, here's the thing. My OneNote, maybe I should stop using OneNote because it is quite buggy. Nice. So let's minus sine squared from both sides of the equation. So if we minus sine squared from the left-hand side of the equation, we're left with the cos squared of theta. And the right-hand side of the equation would be 1 minus sine squared theta. So in order to find sine squared theta in terms of cosine squared of theta, we just take the square root of both sides. So we're leaving with cos squared, or we're leaving with cos theta equals to positive or negative 1 minus sine squared theta. The other way that you can write cos theta in terms of, the other way that you can write sine theta in terms of cosine theta is that you could use the cofunction formula. That way, that also works. But let's just do it this way first. Okay, so now we have a cos theta in terms of our sine squared theta. And we could just use, and we know that, and it says for theta in quadrant 3, so let's just say theta in quadrant 3, let's just do quad 3, and we know, let's draw a unit circle here, our unit circle here, and this is our quadrant 3, because it's 1, 2, 3, and 4, and we know that the x values in quadrant 3, it's negative, so it's our y values in quadrant 3, they're both negative, which means that our tan values in our quadrant 3 is always positive. So let's do our tan theta here. So we know that our tan theta is equals to sin theta over cos theta, and we know that our cos theta is always negative in our quadrant 3, so we just put our negative cos theta right over here, and if our cos theta is negative, our sin theta should also be negative. So we have our cos, I actually did it the opposite. We should be finding our sin of theta in terms of cos of theta. Oh, that's what I did. Here's our sin of theta in terms of cos of theta. Here's our cos of theta in terms of sin of theta, but we actually should do the opposite. So we should do the opposite because we want to write in terms of cos of theta instead of in terms of sin of theta. So let's actually minus cos of theta from both sides of our equation. So we're subtracting cos of theta from both sides of the equation, and we're left with sin squared of theta equals 1 minus cos squared theta. And then if we take the square root of both sides, we have our sin theta equals 1 minus cos squared of theta in its entirety square rooted here. So now we have sin theta in terms of our cos of theta. So now our positive negative sin of theta in terms of our cos of theta. So now we have our function. So, and we also know that our cosine in our quadrant 3 is negative, so is our sine in our quadrant 3 is also negative. So as a result, if we have negative cos theta, we need to have like negative cos theta in terms of our cosine sin theta, and this is our tangent theta. So we have minus and plus. This just means minus corresponding to minus first and plus second. Or whoopsie. This just means that the negative is first, then it's the positive, and we just have 1 minus cos squared theta over cos theta. Alright, and that is our first problem. Let's look at our sample solution for our first problem. It is the same as us. Is it the same as us? Yes, it is the same as us. Yes, we know cos theta is negative in quadrant 3, so we have a negative sign over here for us. Okay, perfect. And we don't need to do anything here on top because we have cos squared of theta. Since cos is negative, since this is like cos is negative, so like cos squared theta is like already positive, so we don't need to like change it. Or sorry, since cos squared is negative, negative cos squared theta is also cos squared of theta, so we don't need to like do anything else. Alright, so this is our first problem over here. And let's move on to our second problem over here. Our second problem asks us to write cos of theta in terms of sine of theta in quadrant, or no, never mind, it asks us to find cotangent of theta in terms of sine squared of sine of theta in quadrant number 2. So we know that cotangent function is 1 over tangent function, which is also cos squared of theta over sine squared, or sorry, cos of theta over sine of theta. This is our cotangent function. And again, we could find this same problem using our Pythagorean identity. I'm just going to write down PI here, Pythagorean identity, without writing it in full because we already wrote an in full for our previous mini set problem. And again, since we are going to write this in terms of sine, so we need to write cos of theta in terms of sine of theta. Again, we just subtract sine of theta from both sides. Actually, I'm really sorry, it's asking us to write it in terms of sine of theta. So we want to isolate sine of theta. I'm doing it the opposite way again. So we are trying to isolate sine of theta, so we subtract cos of theta from both sides of the equation, and then take the square root, giving us sine of theta is equals to the square root of 1 minus cos squared of theta. Okay, so here we have our sine theta in terms of cos theta, and we have actually no, I was originally thinking correct. We are trying to do cos of theta. My fault. Okay, so now let's write our sine of theta in terms of cos of theta. Wait, isn't that what I just did? Or sorry, let's write our cos of theta in terms of our sine of theta. So we subtract sine of theta from both sides of the equation. That was originally correct, but I was confusing myself. And then I take the square root of both sides of the equation. And we have our cos of theta is equals to the square root of 1 minus sine squared of theta. So for our cotangent of theta, we know that is cos theta over sine theta, and our cos theta here is equals to the square root of positive plus minus square root of 1 minus sine squared theta divided by our sine of theta. So now let's look at, and now we know that our angle is in quadrant 2, and here's quadrant 2. We know that sine theta in quadrant 2 is just is positive. So all we gotta do is to write the sine theta here. We don't need to add the negative sign in front of sine theta because we're in quadrant number 2. Okay? So our final answer is actually just positive or negative 1 minus sine squared theta over sine theta. And that is equal to cotangent of theta. Now let's look at our sample solution for our problem number 2. It is correct. So here we just have, let me double check. Yes, they did it the same as us. Which is pretty correct, or not pretty correct, which is correct. Okay. Nice. Now let's look at our problem number 3, which has question number 43. We're writing cosine of theta in terms of sine of theta. this we can just directly employ the cofunction formulae, or the cofunction formula, one of the cofunction formulae. In this case, we can just do, in this case, we know that our sine of theta, we need to write our cos of theta in terms of the, we actually have to write our cos of theta in terms of our sine of theta. So we know that the cofunction formula, our cos of theta, is equals to sine of pi minus 2 minus theta. So this is one of our cofunction formula. And this actually directly just completes this question. So just mention that the cofunction formula states that cos of theta is equals to sine of pi over 2 minus theta, and that is cos of theta in terms of sine of theta. In this case, it says that theta is in quadrant 4, but this function is one of the identities, or I should say cofunction identity. I'll just call it a formula, it's fine. So this function, you don't need to consider which theta, which quadrant is the angle in, because this function works for just for any value of theta, because it is one of the formula. Okay, so here's our 43rd problem. Now let's look at our problem 44. In this case, we're writing secant of theta. We're writing secant of theta in terms of sine of theta. So first, we know that our secant of theta is equals to 1 over the cos of theta. 1 over the cos of theta. The cos of theta. And we're trying to, again, write our cos of theta in terms of our sine of theta. So we're trying to write down our cos theta in terms of our sine of theta because we are asked to write secant of theta in terms of sine of theta. I think we already did this before, so we know that our cos of theta is equals to positive or negative 1 minus sine of theta squared. So our cos of theta is just equals to positive or negative 1 minus sine of theta squared. And this time our theta is in quadrant number 2 again. Or sorry, our theta is actually in quadrant number 1. So this is where our theta is in. And in quadrant number 1, our cosine is positive. So we don't need to do anything extra. And we can just write down our secant of theta is equals to 1 over cos of theta. And our cos of theta is equals to positive or negative 1 minus sine squared of theta. So we just need to write down positive or negative 1 minus sine of theta on the bottom of our fraction. So this is our secant of theta in terms of our sine squared theta for our problem number 44. You can also do like a simplification, because technically having radicals on the bottom of a fraction is not simplest form. In order to do that, let's just multiply let's just multiply the square root of 1 minus sine squared theta to both the bottom and the top of our fraction. That way we can just move our radical to the top. There's probably some way to further simplify it. No, actually, yes, there's probably some way to further simplify it, but this is sufficient for the case of this problem. I just realized that we forgot to check the sample solution for our problem 43. So let's just check problem 43 and 44 for our sample solution together. Yes, they had the same answer as us for problem number 44, and they also did a multiply, or like I guess a what do you call it? Yes, a simplification for the radicals, and they also just used the cofunction formulas. And there, I think here's supposed to be a subtraction, or here's supposed to be a minus sign. Yes, you can vaguely see it in very faint gray. I really don't like how they put the minus sign or the negative sign in really faint gray, because, I mean, who can see it? I can't. But I'll let it pass this time, I guess, because it was quite obvious. that logically there was a minus sign. All right, now let's look at our 45th problem, and we're asked us to write the secant of theta in terms of our tangent of theta. Whoopsie. In terms of our tangent of theta. This is actually quite straightforward. So let's again use our Pythagorean identity, except this time let's use one of our other two Pythagorean identity. So one of our Pythagorean identities states that secant of theta, or secant squared of theta, is equal to 1 plus tan squared of theta. Again, this is pi. We can also derive this identity using our identity 1 equals to cos squared theta plus sin squared of theta, but I'm just going to give it to you, but it's really easy to derive it if you are interested to know. So here for our 45th problem, we want to write secant of theta in terms of tan squared of theta. In this case, we just need to take the square root of both sides. And we have positive or negative, or secant squared theta is equal to positive or negative of the square root of 1 plus tan squared theta. And that is our 45th problem. Let's check the sample solutions to see how they did the problem. Yes, the same way as us, except they actually derived the Pythagorean identity from the other Pythagorean identity, but it is alright. So this question number is, I'm pretty sure it's supposed to be 46 based on logic, but I guess 245 is okay. So just do it in bracket 45, but it is the problem. It is should be problem question number 6, problem number 46, instead of problem number 45. Okay, so right over here, let's do our 45th or our 45th problem, and we're trying to write our cosecant in terms of our cotangent function. Similar to our previous question, our cosecant function is actually also a trick, or is also part of one of the 3 Pythagorean identities, where our cosecant of squared of a function of an angle is equal to 1 plus our cotangent squared of an angle. This is another Pythagorean identity. Let's write it over here. So in this case, if we want to find cosecant of an angle in terms of the cotangent function, which is to take the square root of both sides, which is equal to positive or negative the square root of 1 plus cot of theta. All right, so let's look at the sample solution for question 6. Perfect. Again, they try to derive this Pythagorean identity using our sin squared theta plus cos squared theta equals to 1, which is just, again, straightforward to do because you just need to divide both sides by sin squared of theta. But this question is also correct. So, and woo! Finally, we finished 6 problems, although they're like one big question. So let's just say excellent solution and amazing job. You're correct. Or I guess let's just say excellent solution. It is correct. It's correct. And amazing job. All right. So let's just say solution is correct and move on to our next problem. Problem number 3. Okay, this is another trick problem. We're having a lot of trick today, or we're doing a lot of trick today. So it is asking us to find the exact value of the expression cos of 25, cos of 20, minus sin of 25, and sin of 20. When you immediately look at this problem, you might be like, oh, we have 25 degrees and 20 degrees. they're not angles of the special triangle. So is this probably going to get really complicated and we have to like do some fancy stuff or use a calculator? The answer is actually no, but you do need to do a little bit of, you just need to use like a formula, and this is one of the sum and difference formula for our trig identities. So this is a preliminary knowledge, but basically the cosine of two angles added together is equals to the cos of this angle plus the cos of the other angle minus the sine of this angle. Let me redo this, because see, this thing does not exist. It's either this or that, but I tend to write this same as this, which is just doesn't make any sense. I don't know why I tend to write it like that, but I do, but it's incorrect, okay? So I wrote down like that again. I don't know why. I think it's just a habit. Probably because this is like one of the Chinese characters. So I just tend to like write that Chinese character, while realistically it is actually math. So this is why I always wrote it down weirdly. Okay, so this is one of our trig identities. And note that here the positive sign is on top and here the positive sign is on the bottom. This is because our cos of A plus B is equals to our cos A cos B minus sine B. Just note the sign change here. Our sine of two angles added together and our tan of two angles added together, they all have like similar expressions like this, but they're like in opposite order for like our sine function. And for our cos or for our tan function, the top is like the two have like the same signs, but the denominator of our tan identity for two angles added together or subtracted together has like the opposite signs. So basically, just remember the signs, which sign is corresponding to which sign of the angles added together, so that you don't get your result wrong. Okay? So from here, we have our cos of two angles minus our sine of two angles. So we know that it's actually cos of two angles added together. So let's just write it down. So that's cos 25, cos 25, cos 20, minus sine 25, sine 20, which is equals to our cos of 25 plus 20 degrees, which is equals to our cos of 45 degrees. Now, since we have our cos of 45 degrees, we also know that 45 degrees is an angle of one of our special triangles. So we can just solve our questions quite directly. We know that for this special triangle that has an angle of 45 degrees, the hypotenuse is root 2, and the two of its sides are both 1, so it's an isosceles triangle. And we're trying to find the cos of our angle, and our cosine of an angle is adjacent over hypotenuse. Our adjacent side, the adjacent side of an angle is 1. The hypotenuse of a triangle is root 2. Since cosine of 45 degrees is in quadrant number 1, where cosine is positive, so 1 over 2 is just our final answer. Let's simplify 1 over root 2 by multiplying root 2 on both bottom side and the top side. So our answer simplified would be root 2 over 2. And that is our final answer of the expression cos 25, cos 20 minus sine 25, sine 20. So to solve this problem, all you gotta do is just use this trig identity. Okay, now let's look at the sample solution. Sample solution, perfect. Sample solution is correct. Yes, great. Let's just say, all right, my keyboard is too low. The solution is correct. perfect. Whew. Now here's our next question that asks us to simplify long 5. The word simplify is actually not used very well over here because long 5 is the simplest form. Long is actually just log with base e, but since e occurs really commonly in mathematics, so we're just giving the number e like a special character representation, which is obviously the letter e, and we're changing log e, and we're taking log e and giving it a special representation, which is long because it happens so frequently. Okay? And so we know that log 5 is basically saying e to the power of 5, or sorry, e to the power of, what is x? So basically it's just saying, it's saying e to the power of x equals 5, and what's x? So that's all it's saying, what's x? Okay? And there isn't really any way to simplify it because this block over here is not a simplification, in my opinion, or just in everyone's opinion. So we can't simplify long 5. So cannot simplify. But what you could do is to find the exact value of long 5, which, in my opinion, the easiest way would be using a calculator, although you can use a linear approximation and approximate it by hand because e is approximately 2.7, and 2.7 times 2.7 is kind of close to 5-ish, although the estimation wouldn't be like that good, but you can have a linear approximation or even a quadratic approximation. But the best way to find the exact value of long 5 is to use a calculator, which is approximately equals to 1.61. So long 5 have the exact value of approximately 1.61. Alright? And that is how we approach this problem. Now let's take a look at the sample solution. Yes, they mentioned the same thing as us. So that's the solution. The solution is correct. Oh, whoopsie, I pressed the wrong button. So let's just say correct solution, and that the solution is correct. Here we go. Now let's go to our 5th problem, our problem number 5. This problem is asking us to find the square root of 484. So we're trying to find the square root of 484. And how we approach this problem is to use prime, factorization. And that is how we approach this problem. We're basically trying to find all the prime factors of this number, of this integer, multiply together. So from there we can find pairs of prime factors. So we can find the perfect squares, and then we can find the not the exact value, but we can simplify this radical. Okay, so any number ends with 2, 4, 6, 8, or 0 is a multiple of the number 2. Since 488 ends with 4, we know it's a multiple of 2. So 484 is equal to 2.242, and 2 as well is factors. Since the number 242 ends with 2, we know the number 242 is also a multiple of the integer 484. So we have 2 times 121 as prime factors of 484. Next, we have the number 121, which is not prime, by the way, but its prime factor is actually 11 times 11, which might not be that easy to see unless you have it memorized. But 121 did appear somewhat often in like a talk after grade 9 for math, so it's probably better to like just memorize it. Okay, so here are prime factorization. From here, we know that we have pairs of factors. We have 2 times 2 as a pair, 11 times 11 as a pair. So we just put all the pairs together with each other. So we have our pairs together over here. And we know that the square root of 2 squared and the square root of 11 squared is just 2 and 11 respectively. So we have 2 times 11, which is equal to 22. So our 484 is actually a perfect square, and the square root is 22. So if you can't directly see that the square root of 484 is 22, you can just use prime factorization. Let me underline it. You can just use prime factorization to find our result or to find the solution. Okay? So you can use prime factorization to find it. All right. They also use prime. Let's just say, amazing job. This solution is correct. Okay, now let's see what's our next problem. Our next problem asks us, how do we evaluate secant of negative pi? Whoopsie. So our next problem asks us how to evaluate secant of negative pi. So we know that our secant function is equal to 1 over the cosine of an angle, or the secant of the cosine of an angle, or the secant function is 1 over the cosine of the function, 1 over cosine function. So we know our secant of negative pi is equals to 1 over cosine of negative pi. Now let's draw a unit circle. We have our y-axis and our x-axis. So negative pi is our angle over here. This is our negative pi angle over here. So this is our cos of negative pi. Since we know that the cosine value is the x values of the unit circle, and the sine values is the y values on the unit circle, and our x-coordinate, the pi, is -1, and the x-coordinate is the value of cosine in the unit circle. So we know that in this case, we have 1 over -1, because cosine of negative pi is -1, so secant is also equal to -1. Alright, that is just how we solve this problem. You just need to know a little bit about the unit circle. Now let's look at our sample solution. They mentioned about that fact. There should be a negative sign over here. It's probably just really faint and we can't see it. That is correct. Let's just say great solution is correct. And let's say that solution here is correct. Now let's look at our 7th problem. Our 7th problem. The 7th problem, it asks us what is a ray in geometry. So a ray in geometry is basically a line that starts at a point but goes on from that point infinitely. So basically it is a line that has no end. So this would be an example of a ray that goes phew, has no end. This would be another ray that goes phew, goes over a page and go on infinitely. Usually, even though this ray goes on infinitely, we can't draw a line infinitely. So what we do is to put an arrow here at the end of our ray to symbolize that our ray go on infinitely. They're all rays. Okay? So yeah. And 2 of our most common rays that you are guaranteed, or that you probably know about, are x-axis and y-axis of our coordinate geometry. So this is a ray that goes on infinitely into the positive y direction, and here's another ray that goes on infinitely towards the negative y direction. And here is our x-axis. This is a ray that goes on to positive x infinitely, and a ray that goes on to negative x, in the negative direction infinitely. Let me see if I can rotate it. Rotate. Okay, I can't rotate it. Oh, I can't. No, okay, I can't rotate it. No, why notice? Okay, this should be like entirely. Let me just redraw it. Nice. Now it's much more horizontal and vertical, because they're supposed to be like horizontal and vertical versus like slanted. This is a little slanted. But yeah, here's our x, or here's our coordinate plane, our coordinate geometry, or coordinates plane. Yeah, and that is a lot of rays. And that's basically what a ray is in geometry. A really simple concept that is quite useful. Now, let's look at the sample solution, what the explanation gave. It also tells you how to name a ray, but I guess you can do that. But usually you would name, okay, there's an arrow on top. Okay, that's good. So yeah, I guess that's what you can do. And yes, that is also correct. Use of rays. It's better to like explain the plane in my opinion, but it is definitely a really valid solution. Let's just say the solution is correct. Good job. Yeah, nice. Now let's look at our eighth problem. Our eighth problem let's scroll down a little. And this asks us, how do we find the tangent of the arctangent of -1 without a calculator? So we know that the arctangent, or the arctangent of -1, is just like that. So this is the inverse function of the tangent function. This is just like another notation of the same expression. I like to call it arctangent because calling it tangent to the power of -1, it's really easy to gets confused about it with the function 1 over the tangent function, which is the cotangent function, not the arctangent function. They're completely different. Okay? Now, we know that the tangent function, or tan alpha theta, is equals to the opposite over adjacent, which is basically the ratio of two sides. So what we do over here for our arctangent function is that the arctangent of the opposite over adjacent sides of a triangle is equals to the angle. Because this is basically just because tan function or arctangent function is constructed in a way such that the arctangent function is the inverse of the tangent function, and that's why this two thingy works, because that's just how arctangent was constructed. So this is just like a thing that you should know in order to solve this problem. So now, basically, the question is asking you that the arctangent of -1, where -1 is the ratio of two sides, which angle has the opposite sides over adjacent sides equals to -1? For this, it's actually kind of difficult to think, but we do know an angle where its opposite and adjacent side, where the ratio of its opposite and adjacent side is equals to 1, which is quite close to -1. And which angle is that? It's one of our angles in our special triangle. So here, let me just draw our special triangle. So our special 45 degrees triangle, and its opposite side and adjacent side, the ratio is equals to 1. So we know that the arctan of 1, which is OPP over adjacent. So for angle 45 over here, the opposite is 1, adjacent is 1, 1 on 1 is equals to 1, and this is our 45 degrees angle. Now, we just need to use unit circle to find where the angle, to find where arctangent would be -1. So in order for arctangent to be -1, we need to find the quadrant such that the sine value has the opposite sign of the cosine value, because tangent function is equals to sine over cosine. And we also know that on the unit circle, our sines are y, our cosines are x, they have the same value. So we need to find the part of the circle where the y-axis is positive and the x-axis is negative, or vice versa. And that would be the quadrant over here, quadrant 2, and the quadrant over here are quadrant 4. So our quadrant number 2 and our quadrant number 4. These are the two applicable. These are the two quadrants that applies to our description. However, only our quadrant number 4 is applicable because the arctangent function is only defined in quadrant number 1 and quadrant number 2. Why is that? That is because we need to find the arctangent, or that is because, as we mentioned previously, our arctangent function is constructed based on the tangent function, and our tangent function is not a one-to-one function, and it doesn't pass the horizontal line test, which means it doesn't have an inverse. But how did we have an arctan function? Because we restricted the domain of the tangent function, so basically it means that the tangent function has like a lot of repetitive portions, and we took a little portion of the tangent function so that the function can be one-to-one for this little portion, and we find the inverse of this little portion of tangent function, and that is our arctangent function. So our arctangent function is actually restricted to between -pi/2 to pi/2. You might encounter other restrictions, but -pi/2 and to pi/2 is the most common restriction for arctan function, for the range of the arctan function. So we know that here would be our, or let's do -90 degrees to positive 90 degrees, because we're using 45 degrees angle here above. So let's just convert it to radians, or sorry, let's just convert the angles from radians to degrees. So we know that only -45 degrees, which is over here, is between -90 degrees and 90 degrees. So we know that arctan is equals to -45 degrees. So only our angle over here, our -45 degrees angle, is in between, is the range of arctangent function. So we would know that the arctangent function of -1 is equals to -45 degrees. Perfect. Now let's look at our sample solution over here. Our sample solution on the left-hand side. Perfect, perfect. Equals yes, that is correct. That is correct. -pi/4 or -45 degrees. Perfect. Correct solution. Nice. Now let's move on to our ninth problem. Our ninth problem, problem number 9. And it's asking us how to convert 0.8333 as a fraction. So they only wrote 0.83 to 1, 2, 3 for like three digits, but I'm assuming they meant 0.83, and where the 3 is repeating infinitely, but it's hard to like do the notation, do the bar on top of the number in like on your laptop. So so that's what they put, but I'm pretty sure that's what they meant. or I guess I'll do both. Yeah, but from 0.83333, you just need to know this is the 10,000th place, 10,000th place. So that is just equals to 10,000 as a denominator, and the numerator is everything to the right of the point. So we have this as its fraction form, but I'm pretty sure they're meant this. So let's just do the other one. So how do you convert a infinitely repeating fraction into a, or sorry, how would you convert a decimal that has a infinitely repeating kind of digits at the end of it into a fraction? What you do is you just do some simple algebra, and then that is probably the easiest way to convert it. So first, let's write down our x. So let's have our unknown x, where x is a fraction. Or I guess we can just have our x and set our x equals to 0.883. And then let's times 100 on both sides. So 100 times x is equals to 83.3, where this 3 is repeating infinitely still. So here we have our 100x. Next up, let's times 10x on both sides of the equation from here. And this is our first, and this is our second. So our 10x is equals to 8.3, where the 3 is repeating infinitely. And then let's do our first minus second. So first minus second, which is equals to 100x minus 10x. Let's just erase this. This is a little confusing. So we have 100x minus 10x equals to 83.3 minus 8.3. And here, you would notice that the infinitely repeating 3's at the end of our integers, or sorry, the infinitely repeating 3's at the end of our fractions, of our decimals cancels out with each other. So this infinitely repeating 3 cancels out with this infinitely repeating 3, and we just have 83 minus 8, which is 75. And on the left-hand side, we have our 90x. Then we just divide both sides by 90. And here we have our fraction. Woohoo! Except we still need to simplify it because the smallest common factor of our numerator and denominator of our fraction is not 1. And I think you can divide both sides by 5. So 90, or so let's do 75 divided by 5, which is equals to 15. 90 divided by 5 is equals to 25. We can divide both sides by 5 again. So let's do 15 divided by 5 is 3. 25 divided by 5 is 5. Perfect. That is our sample solution over here. Okay? So 0.83, where the 3 is repeating infinitely as a decimal, is 3 over 5. No, that's not right. Okay, we did something wrong. I'm not sure where for now, but it's not 3 over 5 because 0 over 5 is 0.6, which is not 0.83. Okay, so let's come back to over here. Multiply both sides by 100, which is 83.3, that is correct. Multiply both sides by 10, which is 8.3, which is also correct. 83 minus 8 is equals to 75, that is also correct. We divide both sides by 90, which is also correct. Okay, now let's divide 75 by 5. That should be 1. That should be 15. Let's do 15 times 5. That is 75, correct. Let's do 90 over 5, which is equals to 1. Okay, see, here's where I did it wrong. Because 90 over 5 is equals to 18. It's not equal to 25. Okay, so whenever you reach your final result for math, you need to double check your result to see if that makes sense. Just do a quick mental math. In this case, I double checked my result and it's incorrect. So I just go back and go through my steps to double check everything and see where I did wrong. So now I found where I did wrong. I'm just going to keep going till I get a correct solution. So yeah, this is just make sure to double check your solution for math in case to like make sure that you have your correct answer. Okay, now we can divide both sides by 3 again. So let's do both sides by 3, which is 5/6. Now this answer looks much better. Let's double check over here to see whether 5/6 is 0.3. Perfect. Or sorry, whether 5/6 is 0.83, and this is correct. And it is. So our solution now is finally correct, and our 0.83, where the 3 goes on infinitely, is 5/6. Now let's look at the sample solution. They just did it using this way. I think you really are supposed to put down both because it's, although like the question asked was 0.8333, but you kind of have to, think about it more logically. Include solution for 0.83 where the 3 goes on infinitely, because we are unsure whether unsure about the specific solution needed. In brackets, the answer is 5/6. Okay, let's just press this button to make them to go back and double check. Okay, now let's move on to our next problem. And our next problem just asks us, what are positive numbers? So positive numbers are basically numbers that are greater than 0. So for example, our 5 is a positive number because it's greater than 0. Our 11 is a positive number because it's greater than 0. Our negative 3 is not a positive number because it's not larger than 0. Our negative 13 is also not a positive number because it's not larger than 0. Our 3.1 is a positive number larger than 0. 3/5, positive, larger than 0. Negative 1/2, not larger than 0. And lastly, our 0 is actually not a positive number because positive numbers are strictly larger than 0. And 0 is not larger than 0 because 0 is equal to 0. However, when we are talking about non-negative numbers, that equals 0 because 0 is not negative either. However, when we say non-positive numbers, that also includes 0 because 0 is not positive. So yeah, 0 is not a positive number, but 0 is non-negative and non-positive at the same time. Alright? So yeah, that's all I'm going to cover about positive numbers. Cool. Let's just say great, or the solution is correct. Cool, solution is correct. Move on to the next problem. The next question is, what is a negative angle? So I'm pretty sure you're talking about it in terms of trig. So trigonometry. In trigonometry, when we have a unit circle, the angles that you and here's where the starting place of our angle. When you go counterclockwise through the unit circle, all of your angles is positive. However, when you go clockwise on the unit circle, those angles are negative. So basically, clockwise angles are negative angles, or negative angles are clockwise angles. So basically, when you go clockwise, when the angle goes clockwise, it is negative, because positive angle, because angle is a scalar, so I shouldn't say that. Ignore what I said because it's more in the context of other stuff, and we're talking about math. But when you go counterclockwise, the angle that you go counterclockwise is positive, and when you go clockwise, the angles are negative, because the negative sign is actually indicating the direction that the angle is going. Okay? So basically, negative angles are clockwise angles. Okay? Nice. They just talked about the unit circle. Cool. Let's just say, good job, and say the solution is correct. Nice. Now let's move on to our 12th problem. Why does tan of pi equals to 0? Now let's see, we have 3 more minutes. Okay, I'll just quickly explain this problem. So why does tan of pi equals 0? Tan of pi equals to 0. So this is because our unit circle, so pi is 180 degrees. As we said before, pi is positive, this angle is positive, so we go counterclockwise. So we reach this point on unit circle. Since we know that the cosine or the axis on the unit circle is, or the axis on the unit circle is the cosine, and the y-axis on the unit circle is the sine. And we know that tan of pi is equals to sine of pi, because tan of a function is equal to sine of a function over cos of a because the tan function is equal to the sine function over the cos function. So our tan of pi is equal to sine of pi over cos of pi. And in this case, at the angle pi, our x coordinates, which is our cos value, is equal to -1. Our y coordinates, which is our sine value, is equal to 0. So this is the value of our tan over pi, 0 over -1, which is 0. And that is why our tan of pi equals to 0. You know it based on some facts from the unit circle. That is the easiest way to think about it. There's another way to think about it where you can actually draw the tan graph that plotted on the I guess you should do on the plane where when x is equals to pi, you have tan of x equals to 0. That's another way of finding that tan of pi equals to 0. There's a lot of ways to think about it, but this way about the unit circle is probably the easiest, and that is why tan of pi is equals to 0. Nice. Now looks like the sample solution. Yes, they also mentioned about the unit circle. Let's just say correct solution. Correct solution. Perfect. And the solution is correct. Nice. Now, I think that should be the end of our live stream. If you liked the video or the live stream today, and you like the problems that we went over, today I think we did exclusively trig problem, or at least a lot of trig problems. Okay, not exclusively trig problem, but a lot of trig problems. Okay, so if you like the popular question asked today, or you like the live stream today, feel free to click the subscribe button. Then you can get a notification about when we're going to do our future live streams. Thank you for coming to our live stream. Thank you for coming to our live stream today with OneClass. I hope you enjoy your time here and have a wonderful day or have a wonderful night, depending on where you are. Okay, so I'll just see you next